In the last lecture, we had described basic Rayleigh-Schrödinger perturbation theory in quantum mechanics. In particular, we had considered the non-degenerate case, and we had figured out explicit formulae for the first order energy correction and the wave function correction to first order, as well as second order energy correction. Today, first we will apply those results to a particular specific system and see how those results translate for this particular calculation. So the system we have in mind for that is the anharmonic oscillator. The quartic oscillator, to be precise. Its Hamiltonian is given by the familiar terms for the harmonic oscillator, p square by twice m plus half m omega squared x square. But in addition to this, it also has an additional term, lambda x sub 4, where lambda is a coupling constant. Remember, we had introduced a formal parameter lambda in perturbation theory in the last lecture. This was to keep track of how many powers or how many times the potential was appearing in a particular calculation. Very often, it might happen that the potential already comes with an overall multiplying constant. As an example, lambda in this, we can treat that as something on the same footing as a formal perturbation parameter. Now, just to recall, this problem of course has a very simple, exactly solvable H0 Hamiltonian, which is just the first two terms here, the terms in blue, and this, as we all know, can be rewritten in terms of the raising and lowering operators in this particular form, h cross omega times the number operator a dagger a plus half. And of course, a and a dagger are the familiar raising and lowering operators for a harmonic oscillator. And as you all know, you can just add these two expressions for a and a dagger. That will give you an expression for x. And using that, you can rewrite the perturbing potential lambda x sub 4 here in this form. So this is the final form which will be useful for our calculations subsequently. So let us try to figure out exactly how much will the ground state of the harmonic oscillator, whose energy, as we all know, is h cross omega into half, how much will that energy shift because of this lambda x sub 4 term, and we are going to carry out the calculation to first order in perturbation theory and then to second order in perturbation theory. So let us consider the effect of the perturbation V on the ground state ket 0. We know that the first order energy correction is given by the expectation value in the unperturbed energy eigenstate, namely ket 0, of the perturbing potential. So this is 0 V0 in this particular case, and so plugging in the value for V, we simply get this expression. So what we really need, apart from these constants here, is a matrix element of a plus a dagger whole to the 4, or rather the expectation value of a plus a dagger whole to the 4 in the ground state of the harmonic oscillator. In order to do this calculation rather simply, what we will do is we will first calculate a plus a dagger whole square acting on the ket 0. And as you all know, this sum of two operators, when you square it, you get a square plus a dagger square plus a dagger plus a dagger a. So this operator goes and acts on ket 0. And the result of this operator acting on the ket 0, the ground state of the harmonic oscillator, is pretty simple. After all, a square kills ket 0. A alone kills ket 0. A dagger, well, is actually a dagger a plus 1. And a dagger a kills ket 0 simply because, well, a is on the right, so it's getting to act on the ket 0 first, hence killing it. Remember, the annihilation operator or the lowering operator kills the ground state because you cannot go any further down in eigenvalue. So from these two terms, A dagger and A dagger A over here, what we get is 1 times ket 0. So A squared acting on ket 0 gives you nothing. These two terms together gives you ket 0 back. And A dagger square, of course, raises ket 0 twice to ket 2 with a factor of root over 1 into root over 2. So this is your result. Root over 2 times ket 2, that is the second excited state, plus ket 0, the ground state. So this is A plus A dagger whole square acting on ket 0. But what we need, of course, is the bracket here, bra 0, A plus A dagger whole to the 4, ket 0. In order to get that, all you have to do is remember that if you take the adjoint of this result, you would get the bra 0, A plus A dagger whole square. Actually, A dagger plus A whole square, but that's the same, obviously. So, what we seek, this particular expectation value, is actually nothing but the square of the norm of this vector, because it's the adjoint of this vector acting upon this vector. So it's just this. And because the vector here is this, and we know that the ket 0 and ket 2 are orthonormal vectors, this is pretty easy to figure out. This is just root 2 whole square plus 1 whole square. Hence, it's just 3. And now that we have this result, that this particular expectation value is simply 3, we can plug that back here and we get the first order energy correction as 3 lambda times h cross by twice m omega whole square. Now let us move on to the second order calculation. The second order energy correction formula that we discussed in the last video is En2 is a sum over all states m apart from the state whose perturbation you are talking about. So m is not equal to n here, and that's a good thing because you have epsilon n minus epsilon m. The energy difference between the unperturbed values for the unperturbed Hamiltonian sitting in the denominator here, m equal to n would have been a disaster, and Vmn, the matrix element m bra phi m v ket phi n mod squared in the numerator. And of course, for E02, which we are seeking here, the second order energy correction due to the perturbation to the ground state energy is simply exactly the same, except that n is replaced by 0, and you know that the energy difference between the ground state and the mth state in the harmonic oscillator is simply given by m times h cross omega, and the sum runs over all values of m except for m equals 0. So the sum goes from m equals 1 to infinity. So this looks like an infinite sum, but as we will soon see, most of the terms in this infinite sum, the vast majority of them are actually all 0, because Vm0 is non-zero only for some specific m's. Which ones are those? That's pretty easy to figure out. This time, what we need to do is actually calculate a plus a dagger raised to the 4, the whole operator acting on ket 0, and we do it in steps. It's actually a plus a dagger whole square acting on a plus a dagger whole square. We already know that a plus a dagger whole square acting on ket 0 is given by this, and you have further a square plus twice a dagger a plus 1, which is what the sum of these two terms is, plus a dagger square acting on this whole thing. Now we have to be a bit more careful. The first term is root 2 times whatever happens when this operator or some of these operators acting on the ket 2. A square, of course, lowers ket 2 back to ket 0, so lowers it 2 steps, bringing in factors of root over 2 and root over 1 each time. Twice a dagger a plus 1 simply gives you 2 into 2 plus 1. Remember, a dagger a is a number operator, so it of course gives you back the number eigenvalue. So that's 5 times ket 2 back, and a dagger square acting on ket 2 of course raises it to ket 4 with a root over 3 into root over 4 as a prefactor. Of course, that's what happens when this whole bunch of operators acts on the first term. What happens when the same bunch of operators act on the second term is something we already know, because that's what we calculated in the last step. So this is what you are going to get. Root 2 ket 0 2 lowerings because of a square. 5 ket 2, that's twice a dagger a plus 1 acting on ket 2, plus root 12 root over 3 into 4 ket 4, which is a dagger square acting on ket 2, plus this term, which is our familiar term from the last slide, is just a plus a dagger whole square, this bunch here acting on ket 0. So collecting everything together, we get this. This is a plus a dagger whole to the 4 acting on ket 0, and if we take the overlap of this, or let the bra m act on this from the left, we can immediately see from the orthonormality of the harmonic oscillator energy eigenkets that this particular matrix element, which will go in the numerator here, Vm0, apart from the overall multiplying factors, is simply twice delta m0. So if m is 0, this is the term which will contribute, plus 6 root 2 times delta m2 plus root 24, this factor, times delta m4. So there are only 3 values of m for which this particular matrix element does not vanish, namely m equals 0, m equals 2 and m equals 4, of which m equals 0 does not appear in our calculation. So we are only interested in m equals 2 and m equals 4. So for m equals 2, the numerator will essentially have 6 root 2 whole square, that's 72, and the denominator will have a 2. Of course, the other factors like 1 by h cross omega and whatever prefactors are there in front of v will all be there. But apart from that, the specific contribution from the state from m equals 2 is going to be 72 from square of this divided by 2, and from m equals 4 the contribution will be 24 divided by 4. So that's what you're going to get. This of course is the whole factor lambda into h cross by twice m omega whole squared, because you're squaring Vm0, divided by the h cross omega sitting here with the minus sign and so on. But apart from that, the factor here is 72 by 2 plus 24 by 4, namely minus 42 times this factor. Many books will give you the result for this calculation. They typically use, at least most books use the convention that lambda, h cross, m and omega all set equal to 1. So in such books you will get the second order energy correction as minus 21 by 8. 8 because it's actually minus 42 by 16. And let us wrap up the calculation for this particular problem, the quartic anharmonicity in the harmonic oscillator, at least for the time being. Let's wrap this up with the calculation of the first order energy eigenket. So psi n1, what exactly is that? For that we need these matrix elements phi m with psi n1. So these overlaps really are simply components of psi n1 in the direction of phi m, and from perturbation theory we already know that they have to be Vmn by epsilon n minus epsilon m for m not equal to n. Let me remind you that perturbation theory, that is Rayleigh-Schrodinger perturbation theory, does not tell you what this overlap will be for m equals n. For the harmonic oscillator ground state, of course what we need, well, ground state which used to be the ground state for the harmonic oscillator without the perturbation, the wave function correction for that psi 01 to first order has this overlap with m, namely minus v m0, and epsilon n minus epsilon m is simply minus image bar omega. So this is essentially similar to the calculation we did a while ago, except that there you had Vm0 mod square in the numerator. So this is what you are going to get, and what we need is this particular matrix element which we actually have already calculated. So the only non-zero values are when m equals 2 and m equals 4. Of course m equals 0 is also non-zero, but we don't need that because this formula for the overlap is valid only for m not equal to n. So we get these two factors. The root 18 and root 3 by 2 are simply the factors we had seen in the last calculation. So psi 0 1, apart from this overall factor minus lambda by h cross omega into h cross by twice m omega whole square, is simply going to be 3 terms, root 18 times ket2, that's the projection in the direction of ket2, root 3 by 2 into ket4, plus ket 0 into something, and we don't know what that something is. Only thing we know about that something is that if we use intermediate normalization, this coefficient has to vanish. But if you use conventional normalization, for details just refer back to the last lecture, this factor will be simply I alpha, a purely imaginary number. So this result is indeterminate to an extent. It does not tell you exactly what this alpha is. As far as we are concerned, it could be any purely imaginary number I alpha with real alpha. And as I have kept on assuring you before, the fact that you do not know the first order energy eigenkette does not affect any physical result further. Well, we know the first order energy eigenkette almost completely. We just don't know a small piece of that, but that will not affect your final result. Now, let us move on from this particular example for the time being and talk about a result which is not that well known but deserves to be. This is so-called 2s plus 1 rule for Rayleigh-Schrodinger perturbation theory. And in order to understand what this rule is saying, let us go back to the original perturbation formulae. This is the perturbation equation, the equation you get for the mth order, that is, if you match the coefficient of lambda to the m in h0 plus lambda v acting on psi n is En times psi n, and expand out both sides, this is what you are going to get. H0 doesn't have any lambda with it, and you get psi n m, the mth order piece. H0 acts on that to give you a lambda to the m term. V on the other hand comes with 1 lambda, so it has to act on psi n m minus 1 to get lambda to the m. On the other side, epsilon n is simply En0, no lambdas here, all the lambdas come from psi n m. En1 comes with 1 lambda, it pairs up with psi n m minus 1. En2 pairs up with psi n m minus 2 all the way down the line until En m, the mth order energy correction, has to multiply psi n 0, which we know is phi n. Remember, we are doing non-degenerate perturbation theory here. So we are assuming that corresponding to the energy eigenvalue En0 equals epsilon n, one and only one energy eigenkette for H0, which is phi n. So psi n0 is known to be phi n here. As we stressed in the last lecture, and as we are going to see in the next one, degenerate case is a bit more complicated, but for the timing we are sticking to the non-degenerate case. As we have seen in the last class, if you want to find out the energy correction to mth order, all you have to do is hit this equation, both sides of this equation, with a bra corresponding to phi n. And if you do that, this term, bra phi n h0 psi n m, bra phi n h0 is exactly epsilon n bra phi n, and so this term and this term exactly cancel out, and En m just turns out to be phi n v minus En1. I've just moved this En1 term to the other side, psi n m, and all these other terms beyond this first order term En1 and before En m, so Enj, where j runs all the way from 2 to m minus 1, Enj bra phi n get psi n m minus j. So this is simply the standard way in which you find out the mth order energy correction. Now the standard way seems to imply one thing. Suppose I know all the energy corrections and the wave function corrections up to the order s. That is, I know this for all m minus 1 until m minus 1 equals s. when I say up to, I mean I know all the lower energy corrections already. So I can easily find out the s plus 1th energy correction. So in order to determine the s plus 1th order correction to the energy from this formula, it appears that I will need psi ns here, so the sth order wave function correction, and this sum, well, since I'm putting m equals s plus 1, this sum goes all the way up to s, so I will need all the ens up to ens. Right? So if you are going to directly calculate the energy correction from this formula, this seems to be the best you can do. In order to get s plus 1th order energy correction, you need every correction till the previous step. It so turns out that if you know all the energy and wave function corrections to the order s, not only can you calculate the energy correction to order s plus 1, you can do much better. Then actually determine not just the s plus 1th order correction, but the order 2s plus 1 energy correction. This is behind the nomenclature here, the 2s plus 1 rule. So notice that this actually is quite important, because this is telling you that suppose I know En1 and psi n1, the energy correction to the first order, the wave function correction to the first order. If you just look at this formula directly, it seems to imply that you can use it to calculate En2 and that's it. The 2s plus 1 rule tells you that if you are clever enough, you should be able to figure out even En3 from just knowledge of En1 and psi n1. Similarly, if you knew En1, psi n1, En2, psi n2, the energy and wave function corrections to not only the first order, also the second order, then the formula that we have written down here apparently will tell you En3 only. It so turns out that from this knowledge you can actually work out all the way up to En5. Not only En3, En3, En4, En5 can be found out without your having to calculate any further wave function correction. So let's see how this 2s plus 1 rule comes about. For that you have to realize that in this expression, apart from these overlaps, which should not really be that important. Remember, if we were using intermediate normalization, then all these terms would have been 0 anyway. So we don't really expect much of trouble coming from here. If you are using conventional normalization, these terms will not be 0, but we don't expect our convention, whether we are using conventional normalization or intermediate normalization, to change results for the energy eigenvalues. So we expect these terms not to be too much of a problem. But notice that we are looking at this particular matrix element between psi n0 on the left as a bra psi n0 and the ket psi n s if you are looking at En s plus 1. If you are looking at En2s plus 1, this will be psi n0 and this will be psi n2s. So all we have done here is written down the perturbation equation for the mth order up here, and using this what we will do is we will try to rewrite psi np, psi nq here, where p we have assumed is less than q. After all, in our example we had psi n0 sitting here and psi n2s sitting on this side. So we are just going to try to rewrite psi np, psi nq in a more symmetric way. Notice that you had only psi n0 on one side and psi n2s on the other. But somehow if I could bring up the psi n0 to psi n1, psi n2 and so on, and at the same time bring down the psi n2s to psi n2s minus 1, psi n2s minus 2 and so on, we will sort of meet somewhere in the middle. And that is the basic idea behind this 2s plus 1 rules derivation. So let us see what we are doing here. We start with this matrix element. I've deliberately put in a bracket here and written these two terms in blue to show that we are trying to say psi np is getting acted upon by V minus En1. So the bra getting acted upon by the V minus En1 operator, which is also the adjoint of V minus En1 operator. This is Hermitian. So in order to figure out what this is going to be, we are going to just look at V minus En1 psi n p here, of course move everything else to the other side, and then take the adjoint. So change all the kets to bras and all the operators to their adjoints, all their numbers to the complex conjugates, but here the operators are Hermitian operators, all the numbers appearing epsilon n, e n, j, etc. are real. So frankly not much of a change except for kets becoming bras. So basically this bracket in blue simply becomes this bracket. So all we have done is move this term to the other side, so it becomes epsilon n minus h0 and psi n p plus 1. Here you have psi n p, so with m minus 1 you had m, here you will have p plus 1. And of course the same thing happens here. So m you have p plus 1 minus j, so m minus j, and the upper limit here instead of being m is just p plus 1. So this is what you have. This of course splits up into two pieces. The first piece, psi n p plus 1 epsilon n minus h0, psi n q is a matrix element similar to the previous one, except that it's a matrix element of a different operator, plus a bunch of overlapping terms which comes from this. Now you can easily realize that I have put in a bracket here and written these two terms now in red, simply to emphasize that I am going to use the perturbation equation again to rewrite epsilon n minus h0 psi n q, and that's pretty straightforward. It's going to be V minus En1 psi n q minus 1 minus a bunch of minus, because this is going to move to the other side, bunch of terms from this. So if I do that, this one is exactly what you had already, and now you have a psi n p plus 1, the bra sitting on the left, and the bracket here expands out using the perturbation expansion into this. But notice what has happened. You started with a matrix element of V minus En1 between psi n p and psi n q, and here, apart from this bunch of terms which are just matrix elements times energy corrections, you actually end up with the matrix element of V minus En1 but between psi n p plus 1 and psi n q minus 1. So our job of trying to sort of make this more symmetric, you started, remember, with psi n 0 and psi n 2s. Now you can raise this 1, lower the other side by 1, and then keep on doing it. So basically this is what our equation turns out to be. Psi n p psi n q matrix element, so pq matrix element of V minus En1 happens to be related to the p plus 1 q minus 1 matrix element of V minus En1 with these additional terms. And if we keep on repeatedly use this over and over again in this term, remember phi n is psi n 0, and we will keep on repeatedly using this, we are going to end up with this 2s plus 1 rule that we have been talking about. So just to illustrate that, let's try to calculate En3. This equation up here is simply the relationship that we have derived right now. I have just written it on top here as a reminder so that we can follow the steps that are going on. Now let's calculate En3 using this. En3 from perturbation theory simply happens to be phi n matrix element of V minus En1 between phi n and psi n2 minus this term En2 phi n psi n1. This is simply something which follows directly from perturbation theory. The phi n of course is psi n 0, and at least because we are doing this for the first time, I have explicitly written that out. But now comes the trick. You use this expression to rewrite psi n 0 psi n2 matrix element in terms of psi n1 matrix element. The 0 goes up, 2 comes down. And so the term in blue here actually gives rise to two terms. One is 0 and 2 becomes 1 and 1, as in this formula. P goes up by 1, Q goes down by 1. In addition, you get these terms. Now notice, which terms do you get? Remember here P is actually 0. So P plus 1 is only 1. So the sum from 2 to 1 means there are no terms from this. No positive terms come from this. but there is a negative term. Q is 2. So there's a j equal 2 to 2 sum, which means there's only one term, minus En2, psi n, p plus 1 is psi n 1, and psi n 0, 2 minus 2. Of course, the term in black here is nothing but what you had in the original perturbation theory formula. Now, you just collect those two terms together, and you're ending up with psi n1 v minus En1 psi n1 minus En2 times, which you have taken common between these two terms, times this sum. Now, if we were using intermediate normalization, then the demand is phi n is orthogonal to each one of the energy corrections. So this is 0 and so is this. So this term would vanish. Even if you are using conventional normalization, which is psi n and psi n, the whole eigengets are normalized. We had already figured out the consequence for that in the last lecture. And the consequence, if you remember, happened to be that this sum is actually 0. Or rather, this overlap term is actually purely imaginary. So this term, of course, vanishes. So finally, the expression that we have for En3 turns out to be pretty simple. Turns out to be the expectation value of V minus En1 in the state psi n1. So remember, psi n1 is the first order correction to the wave function, and you just take the correction piece, find the expectation value of V minus En1 in that. Strictly speaking, this is not really an expectation value, because to be an expectation value, you have to divide it by the norm of this, which is definitely not 1. So strictly speaking, it's just the matrix element between psi n1 and psi n1 of V minus En1, and you have not bothered to normalize or anything. This is just the calculated result. But notice that if I have done my energy correction and wave function correction to first order, this formula tells me that I can calculate En3. So s equals 1 gives rise to 2s plus 1, namely 3. So this is an example, the 2s plus 1 rule. Well, we can apply it for En4 as well. For En4, the basic Rayleigh-Schrodinger perturbation theory formula will give you psi n0, psi n3 matrix element of V minus En1. Of course, psi n0 is nothing but phi n, minus these are the two additional terms, which these are already there in the original Rayleigh-Schrodinger perturbation theory. And then we use our trick of raising P, lowering Q, and this actually gives us two terms, two additional terms, coming from the fact that this is sum now from j equals 2 to q, which is 3. So j equals 2 and j equals 3, two terms come here. This sum is still from j equals 2 to 1, which means there's no positive term. So minus En2 minus En3. Minus these two terms. Of course, you can see that the En3 term simply cancels out, because when you combine these two things together, psi n1 phi n plus phi n psi n1 is 0. So we end up with this result, psi n1 V minus En1 psi n2 minus En2 times this. Now this is not 0 actually, and if you remember the conventional normalization formula that we had derived, it turns out that this thing is actually negative of psi n2 phi n, because phi n psi n2 plus psi n1 psi n1 plus psi n2 phi n turned out to be 0. So this is the final simplified formula we have for En4. Here we have energy correction and wave function corrections to second order, and second order only. Conventional Rayleigh-Schrodinger theory would have given you En3 from here, but using this trick that we have played, we can actually find out En4 even. Not only En4, we can actually find out En5. With En5, of course, you start with this, and there are 3 more terms here, 3 more overlap terms, which comes directly from the Rayleigh-Schrodinger perturbation theory. I'm not going to show you details of the calculation here. You should be able to figure it out yourself. But what we do is 0, 4, we change that to psi n1, psi n3, of course with more terms here. And now you have 1 and 3, And now you still have scope for going further. That is, you can raise this one even further, lower this tree even further, and you get psi n2, psi n2. In addition, you get a bunch of other terms. The terms which you already had in the beginning, plus the terms you get when you change this. In addition, the terms which you get when you change this. When you combine them all together, this happens to be the final formula. I leave this as an exercise for you to work out. Show that this is the result for En5. Notice once again, this formula tells you that if you just know the first order and the second order energy and wave function corrections, you can actually find out the fifth order correction to the energy. So these formulae actually turn out to be pretty important for calculating higher order energy corrections in Rayleigh-Schrodinger perturbation theory. And just as a final example, let us return back to the Quartic anharmonic oscillator. There we had calculated up to first order wave function correction and also calculated the second order energy correction. But because we have the first order wave function and energy corrections, I can just use that result, the result that we had already derived, and the formula that we had just figured out, to find out En3, the third order energy correction. So let me just illustrate that for you. The formula which we had derived, not the Rayleigh-Schrodinger original formula, but the formula that we had derived with our trick, is En3 is just given by psi n1 matrix element of V minus En1. And just to recall, of course this splits into two pieces. The matrix element of V minus En1 times just this. And remember, this is of course not 1. So for our problem where H0 is just a harmonic oscillator Hamiltonian. By the way, if you were wondering why I kept on using capital M for the mass here instead of small m, which is conventional, you must have already got your answer. In calculating second order perturbation theory results or the first order wave function correction, we had to use a sum over some small m, and I did not want you to confuse with that with the mass. So I've used capital M for the mass. So V, of course, in terms of the raising and lowering operators, is given by this. And E01, the result we had already figured out, is 3 times this factor, this P factor here. So now, of course, there is another result. The result that we had found out a while ago is the first order wave function correction. Happens to be given by this. And just to remind you, these two factors, root 18 and root 3 by 2, we could calculate using perturbation theory. But the factor in front of ket 0, the only thing that perturbation theory coupled with conventional normalization told us is that this has to be purely imaginary. So this alpha here is a real number. But any real number is possible. So it appears that in this formula, we can run into a problem, because although we are claiming that we know psi 01, perturbation theory will never tell you the value of this alpha. But let's press ahead anyway. For this term, you need psi n1 overlap times En1, and if you do that, the P factor simply comes from the square of this times this factor which you get. So 4 powers of this from the square of psi 01, 2 more powers from here, so that's why you have power 6. Lambda square from the square of this, another lambda here, that's lambda cube, and h cross omega whole square here. 3 is simply the 3 in E01, and then you need the overlap of this particular thing with itself. That's pretty easy. You just take I alpha times minus I alpha mod square, that's alpha square, plus root 18 whole mod square, that's 18, plus root 3 by 2 whole square, that's 3 by 2, and that's what is the final result here. This term here is simply this. What about V? So notice that we need V. V's may overlap between psi n1 itself. So instead of calculating a plus a dagger whole to the 4 acting on psi n1, all I'm doing is I'm calculating a plus a dagger whole square acting on psi 01. Because these are all, these should really be E01 psi 01. So that's what we really are calculating. So n here is 0, of course, in this formula. And here I've just written down n equals 0 properly. And since we already know what psi01 is, namely here, and we know what a plus a dagger whole square is, it has a square, a dagger a, and a dagger, we can figure out what this will do to psi01 pretty easily, and this is what comes out to be the result. Rather nasty looking result, I agree, but what we will need in the final analysis is the mod square of this times whatever prefactors come from the coupling constant and so on. And it's pretty easy to calculate that and show that psi n1 v psi n1 turns out to be the same bunch of factors in front times 3 alpha square plus 2781 by 2. The great thing here is that the alpha dependence in both this one and this one are exactly the same. So when you subtract the 2 to get en3, the unknown term alpha just drops out of the calculation. And when you subtract this, you get the third order energy correction. It turns out to be this. So it's a pretty straightforward, though somewhat lengthy calculation to get the third order energy correction. You could get the third order energy correction directly from Rayleigh-Schrodinger perturbation theory, but that would take a lot more effort. Of course, you don't really have to stop here. You can actually calculate, say, at least since you already have calculated En2, if you just calculate psi n2, the second order wave function correction, you can use your result to find out En4, En5. So fourth order and fifth order corrections to the ground state energy. You can calculate that pretty easily. Of course, this is not En3, this really is E03. So you would agree that this gives you a way of cutting down a lot of the work in calculating higher order corrections to perturbation theoretic terms. So in this lecture, we have seen a particular example, named that of the quartic oscillator or quartic anharmonicity in an oscillator. And we have also explored a not too well known but fairly important rule which allows you to do certain calculations with somewhat greater ease than usual. In the next lecture, we are going to turn to degenerate perturbation theory, a topic which we had just touched upon in the first lecture. Bye for now.